if we can go to the PDE topic,
Sure.
if we may,
Yeah.
which is, I'm aware that of your first work with Shmuel Agmon and Douglas on elliptic PDEs linear. Do you want to tell us a little bit how you got to work with them, your first time, how you met Shmuel?
In fact, I worked with Agmon on a paper in linear partial differential equations, which was hyperbolic.
Mm-hmm.
And we proved a kind of maximum principle for that. That was one of my very early papers. And then I began working with Douglas on extending known theory for second-order elliptic operators to higher-order operators.
Right.
The theory was the so-called Schauder theory, Schauder estimates.
Mm-hmm.
So we managed to prove that in the interior of a domain, and we started to work on doing the same thing at the boundary.
Mm-hmm.
And then we discovered that Agmon was also working on that problem. So the three of us began to collaborate. And that developed into a rather elaborate, I must say complicated, not elegant theory. But the kind of estimates we developed have been used over and over again by people in the subject.
I mean, this is one of the seminal work in the subject, and it's been...
Well, these are basic estimates which people use, so, yeah.
Indeed.
Although, to my knowledge, almost no one has actually read the paper, except some Russians. I know
You
some
mean the
Russians.
paper of
Agmon, Douglas, and
Nirenberg?
myself. It's very hard to read.
I read it once. I mean, you have more than one with them.
We had two papers,
Right.
yeah.
And I read the first one, actually.
I see.
You
so
can add me.
add
I'm
you
sure
to the
there are
group.
many
You
others.
don't look
but
Russian.
No, exactly. Your work, of course, in PDEs led to a series of inequalities, many inequalities.
Yes,
You wanna reminisce?
I developed a love for inequalities, which I think I got from Friedrichs.
Mm-hmm.
And I think inequalities are at the heart of work in partial differential equations. Yes. And I sometimes say inequalities make the world go round. It's beautiful. I just love it. I hear a new inequality, I'm entranced. I worked on some interpolation inequalities, which I discovered had been done independently by Gagliardo, an Italian mathematician. Right. And they're often referred to as Gagliardo-Nirenberg inequalities. And again, they turn out to be very useful.
Like most of mathematicians in elliptic PDE of the maximum principle, where you worked a lot with the moving plane method and...
Oh, yeah. Yeah, the maximum principle, which says that the maximum of solution of a particular class of equations occurs on the boundary, as you know. That's just a fantastic tool. And Didas and Lee and I used it to prove some symmetry of solutions for certain nonlinear elliptic equations. We used a method introduced by a geometer, A.D. Alexandrov, a Russian geometer. The method was used in a problem in geometry and turned out to be wonderful for doing this analysis for partial differential equations. And since then, people continue to use what we call the moving plane method to solve problems that I find unlikely to be solved using that method, but people keep coming up with new applications of the method of moving planes. I'm really struck by that.
It is
but the method was introduced by Alexandrov.
Yes.
It was later used by Sarin, and then Gidas, Ni, and myself used it.
Alexandrov, I think the paper, you're also very fond of that paper, and you always said it's a pleasure.
It's a beautiful paper,
It's a very...
In fact, Yen Lee and I extended the results of that paper to a more general situation, using the method of moving planes.
There are other topics that really quite fundamental in the theory of PDEs. Many of them are present in your little booklet on linear PDEs or nonlinear PDEs. One of them is the Cauchy-Kovalevsky, where you proved some...
Oh yeah, we extended the from the abstract version of the nonlinear Cauchy-Kovalevsky theorem in an abstract setting. Right. And that had been done before in the linear setting. And in fact, in 1941, a Japanese mathematician, Nagumo, had discovered that in the classical Cauchy-Kovalevsky theorem, where you have a variable time, and you assume everything is analytic in all variables, he observed you don't need analyticity in time. He was the first to observe that.
That's in 1941?
In 1941, and that paper was unnoticed for years. It was published in a Japanese journal during the war. Only many years later did people discover that paper. But anyway, I gave an abstract version, which I thought was nice, but then a Japanese mathematician, Nishida, simplified my version. He threw out one of the hypotheses.
Okay.
Wasn't needed, and so I recommend his version. And he applied it in fluid dynamics.
In fact, for a long time, this was the only way to prove certain local well positiveness in fluid problems.
Right.